In this video, we are going to discuss about initial and boundary conditions along with the steady and unsteady state heat transfers. So far in the previous videos, we discussed we derived the general heat conduction equations in cylindrical, spherical and Cartesian coordinates. All the equations that we derived so far, we obtain with the differential terms like dou square t by dou x square, dou square t by dou y square, dou t by dou t, like that. And such differential equations are need to be solved further in order to get the solutions for such equations when we apply to the case. Suppose the general heat conduction equation in Cartesian coordinates, if applied to a cubical object as a wall, then the differential terms are to be eliminated. We need the equation in plain terms of temperature and heat with respect to the respective dimensions. In order to get them, we need to solve the equations, and for the solution we need these initial and boundary conditions. That is the necessity why we need to learn the initial and boundary conditions. Now let us see the initial and boundary conditions. The initial conditions are those which will gives us the information regarding temperature at the beginning of the heat transfer process. We call that as initial time or the initial moment of time, right? The initial conditions which will gives us the temperature details in a body at the beginning of the time, which means at a time t, small t is equal to 0, what is the temperature capital T of the body, or at a time small t is equal to 0, what is the heat that is given to the body Q. They are known as the initial conditions of the body. These initial conditions are mostly helpful for the transient or unsteady state heat transfer problems. Right? The steady state heat transfer never depends on time. So there is no necessity of using this initial condition for steady state heat transfer. They are mostly useful for transient or the unsteady state heat transfer. We are going to learn what is this unsteady state, what is the transient heat transfer in the next slides. Right? The initial conditions gives us the details regarding the temperature at the beginning of the heat transfer process, and mostly useful for transient or the unsteady state heat transfer process. When it comes to boundary conditions gives us the temperature details on the surface of the body or at the surface of the body. Every body consisting surfaces, at every surface or at any surface, what is the temperature of the body that possessed by the body, that is given by the boundary conditions, and these boundary conditions are helpful for solving the heat transfer process in steady state. This is about initial and boundary conditions. We are going to learn how to use the initial and boundary conditions in order to solve the differential equations in the next videos. For now, the initial and boundary conditions, the details are this. The initial conditions gives us the temperature details at the beginning of the process. The boundary conditions gives us the temperature details at the surface of the body or the system through which heat transfer takes place. Right? Moving on, the next topic is steady and unsteady or transient heat transfer. Right? So the before going to the steady and unsteady state heat transfers, uh, let us discuss like this. The temperature which flows through a body is depending on the space and time variables. Right? We already learned from a Fourier's law of heat transfer that Q is equal to minus K into A into dt by dx, which means Q, the heat transfer rate, is directly proportional to dt, the temperature, change in temperature or temperature, and that temperature now is depends on the space and time variables, right? Which means the heat transfer is directly influenced by the space and time, right? The heat transfer depends on the temperature, and the temperature depends on space and time, due to which the heat transfer may be depending on space and time as well. We can write the above statement as a capital T is a function of x, y, z and t, where x, y, z are the space variables, small t is time variable. Suppose if it is a Cartesian coordinates, then temperature is a function of x, y, z. If it is a cylindrical coordinate, temperature is a function of r, phi and z. If it is a spherical coordinates, the body is in, then the temperature is a function of r, theta and phi, along with time small t. Right? Temperature is a function of the space variables x, y, z and the time t. Moving on, now let us see what is the steady state heat transfer. The steady state heat transfer is simply defined as the change in temperature with respect to time. If is equal to 0, then such heat transfer process is called steady state heat transfer. Also, that can also be defined as the temperature at every point in a body or the system is constant throughout the time the heat transfer takes place, then such a body is said to be under steady state. The temperature should be constant throughout, throughout the time. There should be no change in temperature with respect to change in time, then the body is said to be under steady state. As long as the body is in steady state, we can write this as a dT by dt is equal to 0, the change in temperature with respect to change in time dt. If equal to 0, if there is no change at all in temperature with respect to time, then such a process is called steady state heat transfer. Then the temperature now only become the function of space variables. T is a function of x, y and z. Temperature is a function of x, y, z space variables. It is no longer depends on the time. The steady state heat transfer will uh, if the body is under steady state, the heat transfer rate is constant or the heat exchange rate is constant, and also the change in the internal energy of your body is also constant. There is no change at there is not no variation in change in internal heat generation from your body. The best example for steady state heat transfer is the electrical wires that we have in our homes. The electrical wires mostly made up of copper. The electricity when flows through these wires, the electricity means the flow of electrons. The metallic copper offers some resistance against this flow of electrons, due to which the internal heat will be generated in the cables. Right, the heat is generated now, and that heat is dissipated to the surroundings. As long as the electrons flowing through the wires, their quantity is constant, the heat generation rate is also constant throughout, and so the heat dissipation rate is also constant. Right, as no change in internal energy, the heat dissipation rate or the heat transfer rate or the heat exchange rate is constant throughout. That is considered as best example of steady state heat transfer with respect to time. At any span of time, or at the given interval of time, the change in temperature is 0. As there is no internal heat generation, there is no variation in heat, the temperature remains constant throughout for the given amount of time. So dt by dt will become 0. So the body is under steady state. This is about steady state heat transfer. Moving on, the unsteady state heat transfer, it is quite reverse to the steady state. In unsteady state heat transfer, the body's temperature changes with respect to time. At any point, at all the point, at any point in your body, for the given time interval, the temperature changes. We can write this as a dt by dt is not equal to 0. The change in time with respect to change in temperature is not equal to 0. There will always be some change in time with respect to temperature. Then temperature will become a function of xyz space coordinates as well as the time. As a in a unsteady state heat transfer, the temperature changes, the internal heat energy that is generated is also changes with respect to time. That I said, unsteady state heat transfer is quite reverse to the steady state heat transfer. Right? The example for this unsteady state heat transfer will be the temperature variation of a wall throughout the day. In a day, the temperature varies. In the morning we have less temperature when compared to afternoon. In afternoon we have high temperature when compared to evening, right? Like that throughout the day cycle the temperature varies. If a wall is exposed to the sunshine in a day, then in the morning the wall has less temperature, in the afternoon it possesses high temperature, in the evening again its temperature falls. So from the given span of 8 hours or 12 hours, the temperature changes. There will be some change in temperature with respect to time. So the wall is under unsteady state heat transfer. This is the example for unsteady state heat transfer. Moving on, these steady and unsteady heat transfers may be applied to different bodies having different dimensions. If it is a one dimensional body, then the heat transfer takes place through that one dimensional body. The temperature is only function of one dimension. Let us say that is x in steady state. If it is unsteady state, then temperature is a function of one dimension along with time. If it is a two-dimensional heat transfer, then for such bodies, temperature is a function of two dimensions, x and y. Also, if it is a cylindrical coordinates, as theta, as spherical coordinates are as theta, or the theta phi, like that. Right? I generalized, and here it is written x and y's. If it is unsteady state two-dimensional heat transfer, temperature is depends on two dimensions x and y along with time t. If it is three-dimensional heat transfer, then the temperature is a function of x, y, z, as well as the unsteady state heat transfer depends on these x, y, z along with time t. This is about the steady and unsteady heat transfer and the dependence on the space and time variables by the temperature. Thank you.